Hi, and welcome to another discussion of atmospheric dynamics. In this video, we're covering the vorticity equation. This is the fifth video, and we're going through applications of the scaled vorticity equation. So this is what your scaled vorticity equation looks like. We're down to only two terms, and on the left-hand side, you have a change in vorticity. This is relative vorticity. And on the right side, you have divergence. So we're saying that a parcel will spin up or spin down. Following a parcel, it will spin up or spin down based on the divergence or convergence that a parcel experiences. So, in the last video, we looked at troughs and ridges and the curvature. In this video, we're going to talk about jet streaks. And we're going to look at shear vorticity. So first off, we'll talk about jet streaks. Jet streaks generally are areas where the wind is moving faster in the jet stream, a concentrated region where the winds are moving much faster than the surroundings. And you'll see these on a jet stream chart or on a 300 millibar, 200 millibar, or 250 millibar charts. In any three of those, you'll see an area where the winds are moving a little bit faster than the surroundings. And you can see the jet stream kind of moving from the west to the east coast of the United States, but there's a region where the winds are moving a little bit faster than the surroundings. Those are called jet streaks. So here's a simplistic version of a jet streak. Notice that the arrows represent the strength of the wind. So in the center you have the strongest winds. Upstream the winds are weaker, and downstream the winds are weaker. So in the center the winds are moving the fastest. Also notice that as you move to the north, the winds also decrease in strength, and also as you move from the maximum wind, the center of the jet streak, to the south, the winds also weaken. Now, we're going to assume that there's only shear with this jet streak. A lot of times you also have curvature, meaning that it's sometimes jet streaks are located in troughs or ridges. We're going to negate that fact and just look at the shear. So another way of describing jet streaks is by the type of shear that occurs on the side of the different sides of the jet streak, on the north side and the south side of the jet streak. And to do that, what we're going to do is put a paddle wheel on the north side of the jet streak, about where you see the zeta max. We're going to put a paddle wheel there, and as the air flows, of course, it's going to rotate on that side. And cyclonically, it's going to rotate cyclonically or counterclockwise. So that means that there's a maximum in relative vorticity, cyclonic or positive vorticity, in that region. On the south side, put a paddle wheel on the flow where it says zeta min, and you'll notice that it rotates clockwise or anti-cyclonically. So this is what you normally expect or see with a jet streak in the northern hemisphere. The north side we usually call the cyclonic shear side because that's where you see the strongest cyclonic vorticity. And on the south side, it's the anti-cyclonic shear side. So those are ways that we can name or identify jet streaks. So what happens with jet streaks, the wind accelerates, but the wind is actually flowing through a jet streak. The jet streak itself doesn't really move very fast. It moves only about maybe 50 knots through the jet stream. But as air approaches, it accelerates, moves through, and then spits out the other side, the exit region of the jet streak. So the air is actually moving through these jet streaks. So what we're going to do is we're going to follow a parcel of air. Of course, remember this is Lagrangian, the scaled vorticity equation. So we're going to follow a parcel of air as it moves through a jet streak. And we're going to look at the polar side, and then we're going to look at the equatorial side. So the polar side, which is also known as the cyclonic shear side, we'll see how that changes. So as the parcel approaches the jet max, notice that the shear increases. In other words, the cyclonic or the counterclockwise rotation increases. That means you're getting more or higher relative vorticity because of shear. So the vorticity is increasing with time. So using our scaled vorticity equation, the vorticity is increasing with time. That means it's positive. So looking at our scaled vorticity equation, to make the right side positive, you got a negative. F is always positive, so that means that delta needs to be negative. And negative delta means convergence. So approaching a jet streak on the polar side, we have convergence. And upper level convergence in the jet streak means that you must have sinking motions and lower level divergence. So that causes clear skies. Now as the parcel moves out of that region of maximum vorticity, moving downwind of the area of maximum vorticity, as it moves away, its vorticity is actually decreasing. And using the scaled vorticity equation, if the vorticity is decreasing, that means that the change in vorticity with time is negative. To make the right side of the equation negative, both terms need to be positive. So F is always positive. That means that delta must be positive in that region. A positive delta means that you have upper level divergence. And upper level divergence causes lower level convergence. So when air rises, if it has any moisture, it's going to produce clouds. Let's take a look at the anticyclonic shear, or the equatorial side of the jet streak. The same arguments: as the air approaches the maximum wind in the jet streak on the equatorial side, notice that it's approaching an area of relatively minimum vorticity. I mean, the air is spinning there, but it's spinning more negatively. So it's approaching an area that has greater negative vorticity. That means that it is becoming more negative. So if it's becoming more negative with time, that means that the right side must be negative. And if the right side of this equation is negative, both terms need to be positive, both F and D. That delta, that D, if it's positive, it means that there must be upper level divergence. And upper level divergence causes lower level convergence, which means rising motions. And rising motions produces clouds if there's any kind of moisture. As the air parcel moves away from the area of maximum negative vorticity on the equatorial side of the jet streak, that means that the vorticity must be increasing. It's becoming less negative and more positive. So if it's becoming more positive with time, that means that that right-hand side needs to be positive also. And there's a negative sign out in front. F is always positive. That means that to make that right-hand side positive, delta needs to be negative. And a negative delta means that there's convergence. So convergence in that region causes, in the upper levels, causes air to sink and causes lower level divergence. And when air is sinking, we call that subsidence, and that means that you're going to get clear skies. You'll see this all the time with jet streaks. Now, granted, we're talking about jet streaks in terms of no curvature, but there is curvature also, and that does affect it. But here is a upper level chart, 250 millibars. You can see areas of relatively stronger winds across several regions. There's one on the backside, 100-knot wind reported by an aircraft over Wyoming. And then also you'll see stronger winds moving into Minnesota, and the jet streak moving across Minnesota there. This is the type of precipitation that occurred, and you can see that there's not much going on over Minnesota. We don't have any returns from Canada on this chart. So this is not the greatest example, but typically with jet streaks you'll see rising motion and more precipitation in the regions where you have upper level divergence. We'll talk more about this when we get to jet streaks. We'll cover this again and go through this argument one more time. So generally speaking, you'll have rising motion associated with troughs downstream of troughs, and also in jet streaks on the polar downwind side and the equatorial upwind side, and sinking motions with ridges on the downwind of ridges, and then also with jet streaks on the polar upwind side and the equatorial downwind side. As I mentioned, we'll go over this again just to reiterate it, and we'll use another argument actually to figure out where there's rising and sinking motions with the jet stream. So don't worry if you don't get this right off the bat. There will be another video where we'll cover this again, reiterate this later on in another video. So I hope you enjoyed this video on vorticity equation and jet streaks.